Okay, so now it should work. Okay, so the aim of the lecture today is to determine the structure of these groups k star modulo k star to the p and k plus modulo p k plus, where this funny p is the map x going to x to the power p minus x. It's an endomorphism of the additive group k plus. Okay, so as I was saying, both k star and k plus come with filtrations. So let me explain what those filtrations are. So the filtration on the multiplicative group k star is more familiar. It's a k star contains the subgroup of units, which is O star, right? And this group of units contains what are sometimes called higher units. So U1, U2, these are all subgroups of O star. And how is UN defined? UN is defined as the kernel of the map from O star to O modulo T to the N star. Initially, you have the map from the ring O to the quotient O modulo T to the N. Whenever you have a homomorphism of rings, you get a corresponding homomorphism of multiplicative groups. And that's the map which I've written here. And this UN is the kernel of that map. So another way of saying what UN is to say that it's the set of all elements of the form 1 plus A times T to the N, where A is in the ring O. And here are the successive quotients of this filtration. What is K star modulo O star? It is equal to Z. That's what the valuation VT gives me. It gives me an isomorphism from K star modulo O star with Z. What is O star modulo U1? More or less by definition, it is little k star. What is U1 modulo U2? This can be seen to be isomorphic to the additive group K plus. Here it was the multiplicative group having Q minus 1 elements. Here it's the additive group. It's a vector space over Fp of dimension, some dimension little f, but having Q elements, which is a power of P. It's P to the little f. So that's the filtration on K star. And this filtration will, of course, induce a filtration on the quotient K star modulo Pth powers. Similarly, you have a filtration on the additive group K plus. What is it? So K plus is here all the way on the right here, K plus. It has this subring O, which is somewhere here in the middle. Of course, this O is this ideal T raised to the 0th power. Then you have the ideal T itself, then the square of this ideal, which contains the cube of the ideal, and so on. It goes all the way up to infinity on the left. Similarly, this ring O is containing T inverse. So what is this T inverse? This, you can think of it as the sub-O module of K plus generated by the inverse of the indeterminate T. By T inverse, the ideal T inverse, it's not an ideal of the ring O, it is what is sometimes called a fractional ideal of the field K. A fractional ideal of the field with respect to the ring O, of course. So basically it's an O submodule of K generated by T inverse, where T is the indeterminate. Similarly, this fractional ideal T to the power minus 2 is the sub-O module of K plus generated by T to the power minus 2, where T is the indeterminate. And what are the successive quotients of this filtration on K plus? At each stage, T to the n modulo T to the n plus 1 can be seen to be isomorphic to K. If n is equal to 0, then it is actually equal to K. For n different from 0, you might have to make some choice, choice of a uniformizer or something, but you can always get an isomorphism of these groups. So T to the n modulo T to the n plus 1 can be viewed as a vector space over Fp because K is a vector space over Fp. I don't know, but all of these are vector spaces over Fp in T to the n itself, because we are in characteristic P. I mean, K itself, K plus is a vector space over Fp, and so is O. Everything is a vector space over Fp here. So this quotient is a vector space over Fp, and as such, it is isomorphic to the vector space K over Fp. Okay, so these were the filtrations on K star and K plus. Now let us study K star. Okay, so before we come to the quotient K star modulo pth powers, let me recall what the structure of K star is. So it has two subgroups. The subgroup generated by T, I'm calling it T to the power Z, and this subgroup of units O star. Of course, the intersection of these two is trivial, and together they generate the whole of K star. So if in the additive notation, we would have said that K star is the direct sum of these two submodules or subgroups. And here the notation is multiplicative, but that's exactly what is happening here. And why is it the direct sum? For being a direct sum, you need two things. The intersection should be just the trivial element, and together they should generate the whole of K star. And in this case, they do, because every element of K star can be written as a power of T times a unit. And that thing is unique. That is exactly what it means to say that K star is the direct sum of these two things. Now, the group of units O star itself contains the group of invertible elements of the residue field. The residue field is contained in O. So K star, little K star is contained in O star. And then you have this U1, which last time we had seen is a ZP module in a natural manner. Okay? Although we are in characteristic P, K has characteristic P, F, and all these O star, etc. Not O star, O. O is an FP space, but this O star has this subgroup U1, which is a ZP module. Okay? And did we see it last time, or are we going to see it today? That yeah, so we are going to see today that as a ZP module, it's not finitely generated. So we will determine the structure of U1 as a ZP module, because basically we want to determine the structure of K star. And so K star is T to the Z times O star, and O star is little K star times U1. So everything comes down to figuring out what U1 is. Anyway, modulo pth powers, you are going to get this here, and O star modulo pth powers is little k star modulo pth powers, which is trivial because the GCD of p and q minus 1 is 1. K star, this little k star here is cyclic of order q minus 1. So when I raise everything to the pth, and p is prime to q minus 1, so raising to the power p is actually a bijection of this, it's an isomorphism of this cyclic group, and therefore k star to the power p is actually equal to k star as a subgroup. And therefore the quotient is trivial. But the other factor is u1 modulo u1 to the power p. And that's what we are going to determine today. And that will determine k star modulo pth powers completely. Because we understand this group, this is cyclic of order p with a canonical generator, more or less. And this is trivial. So basically, we have to find out what this group is. u1 modulo u1 to the power p. Actually, we will determine not only the group, but its filtration, u1, u2, u3, etc. All these things are, what are the images of these things in u1 modulo pth powers? Okay, so here is the filtration on u1 bar. So I'm using this abbreviation for u1 modulo pth powers. I'll just call it u1 bar. And inside this, I'll have the image of u2, and I'm going to call it u2 bar. I'll have the image of u3, and I'm going to call it u3 bar. So in general, un bar is the image of un, of the subgroup un of u1, in the quotient u1 modulo u1 to the power p. Okay? So this is the notation. And so the proposition here says that for every n, if that n happens to be prime to p, if it's prime to p, then this un bar modulo un plus 1 bar is really canonically isomorphic to un modulo un plus 1. And this we know is isomorphic to k. So if we are going from, we want to understand the successive quotients in this filtration, right? So if you prove that un bar modulo un plus 1 bar is really the same as un modulo un plus 1, we already know that this is isomorphic to k. So we are determining this quotient at least when n is prime to p. What happens if n is a multiple of p? If n is a multiple of p, then it's even simpler. Un plus 1 bar is really the same as un bar. Of course, un plus 1 is not the same as un. It's only un plus 1 bar, which is the same as un bar. Although these subgroups un, n plus 1 and un, these are different subgroups of u1, they have the same image in u1 modulo pth powers. Okay, that can happen, and it's happening here. And we will actually prove that this is the case. Okay. Okay, so let's prove this. So let's first consider the case when n is a multiple of p. And let's write n equals ps. Then, so what one needs to check is that if I take ups and intersect it with u1 to the power p, that's a subgroup modulo which we are going, right? u1 to the power p is a subgroup modulo which we are going in u1. And the image of ups is going to be ups modulo ups intersection u1 to the power p. So let's compute this. The thing on the left can be seen to be equal to just us to the power p. And ps plus 1 intersection u1 to the power p can be seen to be equal to us plus 1 to the power p. Okay, so this is not at all mysterious. You just write us, an element of us is 1 plus a times t to the power s. You raise it to the power p, you'll get 1 plus a to the power p plus t to the power ps, and that's what gives you this kind of and actually this raising to the power p, I mean, if you take, you consider us plus 1 as a subgroup of us, and then raise things to the power p, you land in ups, or you could raise to the power p first to land in ups plus 1, and then take the inclusion to ups. Of course, this commutes, right? Because ultimately what is happening is you're taking an element of us plus 1, raising to the power p, and considering it as an element of ups. So this diagram commutes. But the commutativity of this diagram gives rise to this whole thing here. This diagram in blue. So that was the thing that we started with. This square is the one we started with. Then, of course, I can take the quotient. So I'll get an exact sequence like this. I can also take the quotient here. So I get an exact sequence here. And then vertically, look at the first vertical column. It's ups plus 1 modulo us plus 1. But us plus 1 is exactly the intersection of ups plus 1 with u1 to the power p. That's what we had noted here. Ups plus 1 intersection with u1 to the power p is us plus 1 to the power p. So the image of this us plus 1 here is precisely the subgroup modulo which I have to go in order to get ups plus 1 bar. In other words, the co-kernel of this map is this. And the co-kernel of this map is this. Okay? And we had also seen that this thing here is an isomorphism. Because, where is it? Did I do it today or? Well, these things have disappeared. That's very strange. Yeah, so maybe I didn't recall it today, but this arrow here, the green tilde here, is actually an isomorphism. So the kernel of this thing here, this is the kernel and this is the co-kernel. And what's the snake lemma tell me? The snake lemma tells me that the map, the connecting homomorphism represented by this red thing here, this here, this sequence is going to be exact. But this is trivial and this is trivial. So this means that this map has to be an isomorphism. This is an isomorphism. That was the first part. In the second part, we have to see what happens when n is prime to p. If it is prime to p, let's write it as p times s plus g, where this g is strictly between, where is it gone? Oh goodness, that's not a good idea. Oh yeah, it was done here. But, yeah, here it is. Anyway, so what has disappeared is what I'd already explained, so that's good. So write n as ps plus g, where this g is strictly between 0 and p, right? Now one can check that un modulo u1 to the power p, not modulo. un intersection u1 to the power p is equal to us plus 1 to the power p. And similarly, un plus 1 mod intersection u1 to the power p is also equal to us plus 1 to the power p. Although these subgroups un and un plus 1 are, of course, different subgroups of u1, the intersection with u1 to the power p is really the same subgroup. Okay? So that's a small verification which one should be able to do. And then, in this case, what we have is this diagram. And if you expand it, you look at this is the co-kernel. This is the co-kernel of this arrow. These vertical arrows are raised into the power p. So, what the snake lemma will tell you. So if you're not familiar with the snake lemma, don't worry, I'll come back to it, and we will talk about it at the end. I'll recall the statement and explain what the maps are. For example, what is this red map here? That's the most mysterious one, right? How can you suddenly get a map like this? That's what is going to be explained next. So in any case, what this one tells you is that this 1 going to un plus 1 bar, going to un bar, going to un modulo un plus 1, going to 1, that's an exact sequence. And that is the same as saying that this modulo this is really un modulo un plus 1. In fact, here you didn't need to use the snake lemma. There's a simpler proof, which is the following. So you have un, and which has a subgroup un plus 1, and which contains us plus 1 to the power p. And un modulo us1 to the power p is un bar, and un plus 1 modulo s plus 1 us plus 1 to the power p is un plus 1 bar. Yeah, here it's written. This is un bar and this is un plus 1 bar. So because of this sequence of inclusions, you have this quotient and this quotient, and the quotient of these two quotients is un modulo un plus 1. That's one of the isomorphism theorems. People kind of sometimes number them and tell you whether it's the first one or the second one. I've never understood how you can always be consistent in this, how all books will agree on the numbering. Anyway, but this isomorphism theorem is something which you people must be familiar with. So this is the conclusion. And so let me summarize what we have learned about u1 bar. u1 bar contains u2 bar, etc., all the way. And u1 bar modulo u2 bar is really isomorphic to k, because it's the same as u1 modulo u2. u1 bar modulo u2 bar is the same as u1 modulo u2, and which is isomorphic to k. This goes on all the way up to p minus 1, where up minus 1 bar modulo up bar is also going to be isomorphic to k. But when I come at an index which is a multiple of p, I get the next one is really the same as this one. Okay. So, and this pattern repeats itself ad infinitum, all the way to infinity. So for k star bar, which is k star modulo k star to the power p, I have just one additional term here, which is, and the quotient here is, of course, z modulo pz, right? Because this is what we have seen. K star is really the same as z times O star, and O star bar is the same as U1 bar. Anyway, so you get Z mod PZ here. Okay, so the corollary is that the FP space U1 bar is isomorphic to K to the power N. This is within parentheses, and these parentheses are important. This means the set of all maps from N to K of finite support. So these are all elements of K indexed by the natural numbers. All families, the K to the power N consists of all families of elements of K indexed by the natural numbers. But each family is such that almost all the entries are actually zero. Only finitely many are allowed to be different from zero. Just as in a direct sum of any finite family of modules, the direct sum consists of families of elements such that almost all of them are zero. Almost all means all with the exception of finitely many. Okay, so I mean, there's some sort of a proof here. What is this? U1 bar is K plus U2 bar. Yeah, that's right. That's because U2 bar is a submodule of or subspace of U1 bar, and the quotient is K, and any sequence of vector spaces, any exact sequence of vector spaces splits. So I can write U1 bar as K direct sum U2 bar. And similarly, all the way up to UP minus 1 bar, I can write it as K direct sum UP bar. Then UP bar is UP plus 1 bar. I mean, that's not interesting. So in any case, I can write U1 bar as K to the P minus 1. I mean, you do it P minus 1 times, right? Plus direct sum UP plus 1 bar. And then you repeat with UP plus 1 bar. So ultimately, you will get U1 bar is equal to K to the P minus 1, direct sum K to the P minus 1, direct sum K to the P minus 1, and so on. Okay? So that's what you have. Okay. So that was about the multiplicative group. And now I have to talk about the additive group K plus and the map P of X. I mean, it's a pity that I'm not able to write on the board because this P is not to be confused with this P. You cannot make, I cannot pronounce the two P's differently. They have to be pronounced the same, right? This one is a P and this one is a P as well. But this one is sometimes called a Weierstrass P because Weierstrass used that notation for his P function, which is a completely different entity from this endomorphism here. This can be called Frobenius minus identity. Anyway, so you have K plus, and then you have this endomorphism P of K plus, which takes x to the power P minus x. That's an endomorphism because x plus y to the power P is x to the P plus y to the P. Okay, endomorphism of the phi of the additive group is what we are interested in. Okay, so as before, let's use this abbreviation K plus bar for K plus modulo P K plus. This is the co-kernel of this endomorphism P. And because K plus had this filtration by powers of the ideal T, K plus bar will have this filtration by images of those powers of the ideal T. So you'll have T0 bar which is the same as O bar, because T0 is O. Then you have T bar and T squared bar, and T to the minus 1 bar, T to the minus 2 bar, and so on. It goes, stretches to infinity in both directions. And we have to figure out what the successive quotients are. Okay, so let's try to determine what Tn bar modulo T to the n plus 1 bar is equal to. Fine. So for the first observation is that T bar is equal to 0. So it's being claimed that this P is actually an isomorphism. So if it's an isomorphism, obviously the co-kernel is going to be trivial. So what do we have to show in order to say that this is an isomorphism? We start with an A in T, and we have to show that there's a unique X in T such that P of X is equal to A. That's what we have to show that it's bijective. And bijective endomorphisms are isomorphisms, right? So this A is given to us. It has these coefficients A1, A2, etc. And this X is what we are looking for. Let's say that the coefficients of X are X1, X2, and so on. Why is there no A0 and no X0? Why is there no there are no constant terms? There are no constant terms because A is in the ideal T. And we are also looking for an X in the ideal T. So there are no constant terms. Or in fact, the constant term is 0 is the more correct way of saying it. Okay. So now for every index n, what is the coefficient of T to the n in Px? You just raise it to the power, you raise x to the power p and subtract x from it. So the coefficients of T to the n is going to be minus x if this n is congruent to 0 mod p, if n is divisible by p. Oh, there's some problem here. This should be not divisible by p. Okay, so it's well, it's ridiculous. The same thing is repeated here, but what is meant is that n should be prime to p. It's not congruent to 0 mod p, and same here. Anyway, so the coefficients of T to the n is minus xn if n is prime to p, and it is xs to the power p minus xps if n is p times s. And that is just a simple matter of verification. Now, what we are looking for are the xn's. And so by equating the coefficients of T to the n with an, you have found your xn's. Xn is going to be minus an, because it's minus xn is the coefficient of T to the n, and the coefficient of T to the n in A is an, so xn is going to be minus an if n is prime to p. What happens if n is a multiple of p, if n is equal to ps? Then this is equal to an, right, or aps. And by inductive hypothesis, we can assume that xs has already been found. So you can take xps to be xs to the power p minus aps. So this is a recursive definition in the case when n is divisible by p. Okay, so this proposition is proved that the image of T bar, or the image of T, namely T bar, is trivial in K plus bar. K plus bar is K plus modulo PK plus, and P is this funny Artin-Weierstrass P. Okay, so, but to determine the image of O, I need to recall some facts about the trace map. And I just need to do it from this field little k to FP. Little k is an extension of FP. It's a Galois extension. And the Galois group is generated by the map, which sends an x here to x to the power p. So the trace Sk from k to Fp is defined as, and it takes x to the sum of all conjugates of x. And the conjugates are x itself, x to the power p, x to the power p squared, all the way up to x to the power p to the f minus 1. It's not f minus 1. It's p to the f, or p to the f could have been called q. So it's q minus 1. And why does this element here on the right, why does it belong to Fp? It belongs to Fp because its pth power is equal to itself. So here is what is being claimed, that Sk of x, this element is being called Sk of x, the trace of x is an Fp because the trace to the power p is equal to the trace. And that's an easy verification. This is what Skx is. I raise it to the power p. Then I'll get the pth powers of all these things. So I'll get x to the power p plus x to the power p squared, all the way up to x to the power p to the f. Because here it was x to the power p to the f minus 1. So here I'll get x to the power p to the f. But that is equal to x, where f is, of course, the degree of k over Fp. So this is really the same as Skx, and it's the same as this, except that this little thing, this thing here was written here in this case. So that's equal to Skx. So this Sk is actually a map from k to Fp, and you can check that it is linear. It's the trace of the sum of two things is equal to the sum of the traces. And that's again obvious because x to the power, x plus y to the power p is equal to x to the power p plus y to the power p. Okay. And next I'll need the fact. So this is the map I have defined, Sk. I claim that it is surjective. That's only the first claim. The second claim is that the kernel of Sk is the image of this little p. I mean, this p can be thought of as a map from k to k as well, right? P, it takes x to the power p minus x. So it can be thought of as it's a map from this little k to itself. And the kernel of this p is Fp. Okay, so I want to show that this sequence here is exact. That's the claim. So by definition, so let's establish that the kernel of this p is equal to Fp. Now kernel of p is the set of all x such that p of x is 0, but p of x is x to the power p minus x. So p of x is 0 means x to the power p is equal to x. Now if you know a little bit of Galois theory, that means that this equation here amounts to saying that this x is fixed under the generator of the Galois group of k over Fp. Maybe this generator should have been called some a going to a to the power p, because x has been used for this element. But it's clear that if something is fixed by a the generator of the Galois group, then it has to belong to the base field. And that the set of fixed points is exactly the base field. Recall, I mean, this is what I had earlier, when I recalled some basics of Galois theory, this is how I'd even defined a finite Galois extension, that the fixed field under the whole group of automorphisms should be the base field. But another way of seeing that the kernel of P is equal to Fp is to say that this P is actually, the kernel consists of zeros of this polynomial, t to the power P minus t. And this polynomial is a polynomial of degree P. So it can have at least P roots in this field K. But clearly, Fp is contained in the kernel of P. Now, the kernel of P has P elements, it contains these P elements, so these two sets have to be the same. And that establishes Fp equal to the kernel of P. Next, I want to show that the image of P here, the image of P inside this is the same as or is contained in the kernel of Sk, of the trace map. Let's show the inclusion first, and then we will show that they are actually equal. So how about the inclusion? The inclusion is a straightforward computation. So I take an element in the image of P. So it will look like x to the power P minus x for some x in little k. And I take its trace and I'll check whether I get 0 or not. So the trace is linear. So I'll get sk of x to the p minus sk, the trace of x to the p minus the trace of x. At this point, if you recall this other definition of the trace, saying that the trace of x is really the sum of all conjugates of x, then you can immediately say that this difference is equal to 0, because the conjugates of x to the power p are really the same as the conjugates of x, because x to the power p is in fact conjugate to x. In any case, even if you don't know those things, you just have to compute, you just have to apply the definition. What is sk of x to the power p? It's x to the power p plus its pth power all the way up to its p to the f minus 1th power. But x to the power p to the power p to the f minus 1 is x to the power p to the f. And then you have the trace of x, which is this here. So many of these terms will cancel each other out, except that this term will remain, and so will this minus x. Okay. So I'll get x to the power p to the f minus x. But x to the power p to the f is equal to x for every x in k, because k has p to the f elements. Okay, so I get 0 here, right? So I've proved this inclusion. Next, let me try to prove that Sk, the trace map, is surjective. Now it's a linear map. So to show that a linear map is surjective, it's enough to show that it takes a non-zero value. It's enough to show that it's not the zero map. Okay, so the trace map, let's look at the zeros of this polynomial. The zeros of this polynomial are exactly the elements of k which have trace 0, more or less. I mean, this is the definition. But this is a polynomial of degree p to the f minus 1, q minus 1. That's the degree of this polynomial. It cannot have it cannot have q zeros, right? A polynomial of degree p minus 1, or q minus 1, excuse me, can have at least q minus 1 zeros in the field k. So there has to be at least one element which is not a zero of this polynomial. In other words, at least one element whose trace is not zero. And that is sufficient for me, because if a linear map takes a non-zero value, it has to be surjective. So that shows that Sk is surjective. Now, I'd only proved this inclusion. The image of P is contained in this. Let me now show that they are actually equal. These two subspaces are actually equal. So, what was the dimension of the image of P? Now, P is a map from K to K, and its kernel is of dimension 1. So its image will have dimension f minus 1, right? Similarly, this Sk, the trace map, it's a map from K to Fp, and it's surjective. So its kernel will have dimension f minus 1. Yeah, because the image is this one-dimensional space. And we have the inclusion. That's what we have proved earlier. So both these spaces these two spaces have the same dimension, and one is contained in the other. Therefore, they have to be equal. That's it. That's how you can prove that two vector spaces are equal, or a subspace is equal to the whole space. If you compute the dimension of the subspace and the dimension of the whole space, and if you find that they have the same dimensions, then of course they have to be equal. Okay, so this is what I needed in order to compute O bar, and I'll just wait for 2 minutes if you have any questions. Okay, if there are no questions, let me continue. Let me compute the image of O bar. So take an element A in O, so it will look like A naught plus B, where A naught is a constant. I mean, and B is in the ideal T. So A is going to be in the image of P, if and only if this A naught is in the image of P, is in PK, little k. So that's a claim, and here's the proof. You know, this B is in the ideal T, so it's equal to P of Y for some Y, for a unique Y in the same ideal T. As P is an endomorphism, and B is equal to P of Y, this A is going to be P of K, in P of K, if and only if A naught is in P of K. That's kind of, yeah, there's nothing much to prove here, really. And so the corollary is that if I take the map from O to K, that's going modulo the ideal T, and then I take the trace map to Fp, the kernel of this composite map is really the intersection of Pk with the ring O. And therefore, the image of O, namely O bar, can be identified with Fp. Okay? So this is really just a translation of what we have been doing, and the only thing which is being used apart from this proposition here is that the image of P on K is equal to the kernel of this trace map. Okay, so you just write down these things, and that's an immediate consequence of what we have been doing. Okay. Right. So, so till now, what we have proved is that this T bar is 0, O bar is equal to FP, and then we have to figure out what these successive quotients are and what these things are, right? So in order to figure out what these quotients are, where the question marks are, so we have to check that this funny P takes the ideal T to the minus S inside T to the minus PS, and it takes the ideal T to the minus S plus 1 into the ideal T to the minus PS plus 1. Okay. So again, this is just another way of just saying that the valuation is multiplicative, and the valuation of a difference is at least, or a sum is always bigger than the smaller of the two, and actually equal to the smaller of the two if the two valuations are different. So, and therefore we get, I mean, I know these quotients, of course, I get an isomorphism with T, and here also I get an isomorphism with, not T, with K, the residue field. Huh? These are, once you have chosen T as a uniformizer, you get a kind of, yeah, here it is, the map is here. This should be A minus S bar, but that's the same as A minus S, right? Yeah. Okay, so you have this commutative diagram, and as a result, I'll prove this proposition, which is the main proposition for determining the successive quotients which are marked with a question mark here and here. So this proposition says that for every index n, T to the minus n intersected with pk is P of T to the minus floor of n by P. So n by P is a rational number, and the floor of a rational number, or a real number for that matter, is the largest integer which is less than that real number. The floor of x plus, floor of n plus 2, where n is an integer, is n, and the floor of n minus 2, where n is an integer, is n minus 1, etc. So this is the statement of the proposition. We, in order to prove it, we consider these two cases when n is a multiple of p, or so that's the case here, and then we will consider what happens when n is prime to p. So let's first look at the case n is a multiple of p. So in that case, if n is a multiple of p, if n is equal to ps, then this is actually an integer, so it's this n upon p is actually s, and therefore what I have to prove is that n t to the minus ps intersected with pk is p of t to the minus s. Now, one of the inclusions is clear, that this right hand side is contained in the left, or okay, the right hand side is contained in the left hand side is clear. So let's take something on in the left hand side. So we take an x in the left hand side, everything. So it's an intersection. So an element of the left hand side will look like p to the x for some x in k, such that p to the x is in t to the minus p to the minus ps. Now, if vt of this x is positive, then x is clearly in t to the minus s, right? Because it's even in t to the 0, I mean if it's positive. And t to the 0 is contained in t to the minus s. Now, but if Vt of x is strictly negative, then you can check that Vt of Px is equal to P times Vt of x. Okay? I mean, that's just, you know what P of x is. It's x to the P minus x. And it's a difference of two things. So, and the valuation of the first one is P times the valuation of x. The valuation of the second one is what it is. And this one is smaller, so you'll have, let's see. This one is smaller because the Vt of x is negative. So, but Vt of Px is greater than minus Ps by hypothesis, because, yeah, here it is, right? So, Vt of x must be at least minus s, which means that x has to be t to the minus s. Now let's consider the case when n is prime to p and write n as ps plus g, where g is strictly between 0 and p. And we have to show that t to the minus n intersected with pk is p of t to the minus s. Because that minus s is what this p, n upon p, the floor of n upon p is s, as you can see, because n upon p is s plus g upon p, but g upon p is strictly between 0 and 1. So the floor of s plus g upon p is equal to s. Anyway, so it's clear, one of the inclusions is clear. P of t to the minus s is contained in t to the minus ps, which is contained in t to the minus n. Conversely, if x is in k and its valuation is negative and p of x is in t to the minus n, then as before you have this, and the valuation of t, the t-adic valuation of x is going to be at least minus s minus g over q. But the valuation is actually an integer. And if it's greater than this, then it has to be greater than minus s, because it's an integer. And this is strict, g upon p is strictly between 0 and p. And this here implies that x is in t to the minus s. Okay. So here's a proposition which is analogous to what we had done for the multiplicative group. It says that if n is multiple of p, yeah, then t to the minus ps plus 1 bar, which is normally a subgroup of this t to the minus ps bar, is actually equal to the whole thing. So you have equality here. That's what the proposition is asserting. Normally you just have an inclusion. But if n is prime to p, then this subgroup is actually, it's a proper subgroup or subspace, and the quotient is actually isomorphic to k. Maybe instead of k, I should have written that it's equal to t to the minus n over t to the minus n plus 1 without the bars, just as we had it for the multiplicative group. Where is it? Yeah, here we had it for the multiplicative. Un bar modulo un plus 1 bar was identified with un modulo un plus 1. Similarly, for these t's, it would have been better to write it would have been better to say here that this t to the minus n bar modulo t to the minus n plus 1 bar is equal to t to the minus n modulo t to the minus n plus 1. So this FP space is isomorphic to this, is a corollary, just as before. Okay, so we need to prove it, right? So let's first look at an n, which is a multiple of p. And then, just as before, we had computed what the intersection of this t to the minus ps with pk is. It's p of t to the minus s. And the intersection of t, and we had computed this as well. So as before, let's look at this square here, the first top left square here, this one. So I'm saying that you have the p map here, the p map here, the vertical maps are p, and the image of this is really the intersection of this with p of k plus, capital K. And so is the image of this. The image of this here is the intersection of this with p of capital K. So the co-kernel is just this, is the one with the bars. So let's look at what is happening. You have this diagram, and you have these co-kernels here, and that this here we have seen is an isomorphism. Therefore, this map here is an isomorphism by the Snake Lemma, because the Snake Lemma says that if the kernel of this map, which is trivial, to, oh goodness, I hope this doesn't disappear. So the kernel of this to this here, to the co-kernels, is an, it's an exact sequence, right? I'll recall what the Snake Lemma is. At the end of the talk, I'll recall what it is. Now let's consider the case when n is prime to p. So you can write it as ps plus g, where s is strictly positive. N is, anyway, and g is strictly between 0 and p. Then we have seen that the intersection of t to the minus n with pk is p to the minus s, and so is the intersection of t to the minus n plus 1 with pk. It's the same p to the minus s. These two are the same here. Whereas when p was a multiple of, when n was a multiple of p, these two were different. These two were different. And there's a typo here. I don't know how to correct this. This is not p to the minus s, which doesn't make any sense. It's p of t to the minus s. Similarly, this is p of t to the minus s. The image of this here. So the image of this here as well, right? So these are p to the minus s is p of the ideal t to the minus s. So you do as before. I mean, this is the square that you start with. These two are the same, and you have the co-kernel here and the co-kernel here. So you have a map between these two co-kernels, and the sequence, this green serpent, green snake, that sequence is exact. So this means that this modulo this is equal to this modulo this. Yeah, this is what it amounts to. And that we have seen earlier is equal to K, equal to in the sense of being an isomorphic, just isomorphic. So here is a picture of K plus bar, which was an abbreviation for K plus modulo PK plus. So it has, all these, the images of T and O and T to the minus 1 and so on, all these images. The image of T itself So these images give a filtration of this k plus bar. And the filtration stops here in some sense. T bar, the image of T bar, T, the ideal T, is 0. The image of O can be identified with FP. And these successive quotients are actually just K and so on. Okay, so this gives you a complete picture. Yeah, so here this goes on till you reach minus P plus 1, and then that is equal to T to the minus P. Okay, so and then it continues. Whenever you are about to reach a multiple of P, you get equality here. Okay, so it remains for me to recall the snake lemma, but before that, I'll wait for a few minutes to see if there are any questions. Okay, if not, let's continue. So the snake lemma. So here you have an arbitrary ring. It doesn't even have to be commutative. And everything is going to be A modules and maps of A modules. All the objects are going to be A modules, and all the arrows are going to be morphisms of A modules. So even before I state the snake lemma, there are these preliminary observations that whenever I have this kind of a commutative square, so I have these 4 A modules and these 4 morphisms of A modules, such that F followed by D is the same as D prime followed by G. That's what it means for this diagram to be commutative, right? Then the first claim is that there's a unique morphism from the kernel of D prime to the kernel of D. So the kernel of D prime should be written here somewhere, and the kernel of D should be written somewhere here. So the claim is that there's a morphism from the kernel of D prime to the kernel of D, which makes this square commute. There's a unique morphism like this. This is more or less obvious. So, but let's prove it. So suppose you have some element in the kernel of D prime. This means that D prime of X is 0, right? That's what the meaning of kernel is. Now, if D prime of X is 0, G of D prime of X is going to be all the more 0, right? If you apply G to 0, you get 0. Because G and all the maps are morphisms of A modules. But G D prime is the same as DF. Look at this diagram here. G D prime is the same as DF. So if G of D prime is 0, G of D prime of X is 0, then D of F of X is 0. Which means that F of X is in the kernel of D. Okay, so that means that this phi just takes an X to F of X. What we have proved is that if X is in the kernel of D prime, then F of X is in the kernel of D. And that's a map, that defines the map phi. And obviously, it makes the diagram commute and is the only map which makes the diagram commute. Similarly, for the same, look at the same square here, 4 maps M prime to M to N, and then M prime to N prime to N. So that square whenever I have a square like that, which commutes, there is a unique map from the co-kernel of D prime to the co-kernel of D, which makes this square commute. So in this square, the co-kernel should be written here, and the co-kernel of this should be written somewhere here. Then I'm saying that there's a map from the co-kernel of this to the co-kernel of this, which makes this diagram, this square here, imaginary square, right? I've not drawn it. Makes this square commute. Okay. So how do I prove that? So, okay. So I have to start with an x in the co-kernel and produce an element in the co-kernel here. So what I can do is to lift x to y and then apply g to that y and then take the image gy bar of this gy. One has to check. So this is an attempt at defining a map. We have not yet defined it. We have not defined it because we haven't shown that this procedure is independent of the choice of y. What if I choose two lifts, y1 and y2? Okay, let's see what happens if I take two lifts, y1 and y2. Both of them go to x. That means that y1 minus y2 is in the kernel of this map to the co-kernel, and therefore it's in the image of D prime, because the kernel, I mean, it's the co-kernel of D prime, right? So y1 minus y2 has to be in the image of D prime. So it's D prime of z for some z in M. So now I've got hold of this z. I can apply f to it, and then d to that f. But this z I know goes to d prime of z, right? And d prime of z goes to g of d prime of z. And these two things are equal because this square commutes. But this d prime of z was equal to y1 minus y2. So when I apply g to y1 minus y2, I'll get g of y1 minus g of y2. Now, the difference g of y1 minus g of y2 is equal to d of f of z. So these two things will be equal to each other in the co-kernel. G of y1 bar is equal to g of y2 bar. So this is actually something which defines the map from the co-kernel of d prime to co-kernel of d. And of course, one has to check that it's a homomorphism. It's a morphism of A modules. And this is a checking which you are perfectly capable of doing. Finally, the statement of the snake lemma. So forget about the things in red for the time being. Just look at the diagram in blue. It says that if I have an exact sequence m prime to m double prime to 0, and an exact sequence 0 to n prime to n double prime, and these vertical maps d prime, d double prime, such that this square and this square, both these squares commute. Then the first claim is that there's a unique morphism from the kernel of this d double prime to the co-kernel of this d prime. There's a unique morphism from this kernel to this co-kernel, such that 1 is taken to 6. So now I have to explain what these red things are. What are 1, 2, 3, 4, 5, 6? Okay, so 1 is an element of the kernel of D prime. Let's call it Z double prime, but I don't know whether I'll need that notation. I'll just call it 1, with the red thing. So this kernel is, of course, a submodule of M double prime, So 1 goes to 2 in M double prime. It's the same element, but sort of as an element of M double prime. Now this pi is surjective. Look at this this exactness. Look at this 0 here. So pi being surjective, this 2 can be lifted to some element 3. Now 3 is not uniquely determined by 1 or 2 is uniquely determined, of course, but 3 is not uniquely determined. Any two choices will differ by an element of M prime. But if I make a choice 3, then I can push to apply D to it and I get an element 4 of N. Then N prime is a sub. Look, but what happens to this 4 if I apply mu to it? If I apply mu to it, it's the same as applying pi to 3 and then applying D prime. But when I apply pi to 3, I get 2. And I apply D prime to 2, I get 0. Because 1 to 2, and then of course it has to be 0 because it's exact at M prime. So 4 goes to 0 in N double prime. Therefore, there's an element 5, a unique element because it's injective. There's a unique element 5 such that G of 5 is equal to 4. So this 5 is uniquely determined by 4, but 4 is uniquely determined by 3, but 3 was not uniquely determined by 2. Now this, so if I take a different element here, let's say 3 prime, then their difference is going to come from this M prime, and the 3 prime will give me a 4 prime, and the 4 prime will give me a 5 prime just as before. But 5 minus 5 prime is going to be D prime of this element which I got from 3 and 3 prime. The element such that F of, I should call it some name, right? What should I call it? So this 3 is not uniquely determined by 2, and therefore any two choices of pre-images of 2 they differ by an element omega, completely arbitrary name, but let's call it omega. So omega, F of omega is 3 minus 3 prime. Then 3 and 3 prime give rise to 4 and 4 prime, which give rise to 5 and 5 prime. And I claim that D prime of omega is equal to 5 minus 5 prime. And therefore 5 and 5 prime have the same image, 6. And therefore, at least I can define this map from the kernel of D prime to the kernel of D double prime to the co-kernel of D prime, which sends 1 to 6. I've defined a map where 3 and 5 are elements having these properties, as I did. So why does 3 exist? Because it exists because pi is surjective. Why does 5 exist? Because 4 goes to 0, and this diagram is, I've explained it there. 4 goes to 0 because it comes from 3, and 3 goes to 2, which goes to 0 because it comes from 1. Okay, and because 4 goes to 0, it comes from some 5, and that 5, of course, is uniquely determined because G is injective, and I take the image of that 5. The only ambiguity was in the choice of 3. So if I choose a different element 3 prime here, they'll differ by an element omega here, and then 5 and 5 prime will differ by D prime of omega, and therefore they'll have the same image. 6 is going to be equal to 6 prime. That defines the map. So the real content of the snake lemma is that this diagram, from the kernel of D prime to the kernel of D to the kernel of D double prime, and delta, this is the snake-like map, which is, it's called delta. It's sometimes called the connecting homomorphism, or liaison is also the term which is used sometimes. Anyway, so this connecting homomorphism delta takes kernel of D prime, D double prime to co-kernel of D prime, which is taken to the co-kernel of D, which is taken to the co-kernel of D prime, and this sequence is exact. So this is the snake lemma. It has been used a certain number of times today. So I thought, for the sake of completeness, I should recall it for those of you who have not come across it. This kind of arguments are not deep and difficult. They are kind of things which you should get used to. And I'm sorry for the internet today. I hope you did get something out of the thing. And let me, okay, since I have a few minutes, let me ask people if you have any questions now. Are there any questions? Yeah? Okay, if there are no questions, let me stop here today and we'll meet on Monday. Okay.